Going to go ahead and get started. It's my pleasure to introduce Greg Lynn, who's been my long-suffering office mate for 12 years now. Greg did a master's at Columbia and worked in two startup companies before coming to the Center for Nanoscale Systems. He started in sort of microfluidics area and has moved into being our X-ray expert. He does the X-ray photoelectron spectroscopy and the micro-computed tomography, X-ray tomography techniques. Today, he's going to focus his talk on the micro-computed tomography. So all yours, Greg.
Okay. Yeah, thank you for our introduction. So again, my name is Greg Lynn, and welcome to this today's imaging group summer seminar. So my topic will be on microcomputer tomography. So before we start, let's review a case study. So this guy is called Shotoku Taishi, so also known as a Prince Shotoku H2. So from Harvard Art Museum. So it's a 13th century Japanese wooden sculpture, and it was known as the oldest and also finest surviving sculpture for the Japanese founder of Buddhism. And it's a hollow sculpture. Inside the sculpture, they contain about 70 different objects like paper, textile, crystal, glass, and some wood elements. And when Rachel from Harvard Art Museum, when she first came to CNS, she's interested to see the interior of the sculpture. So the previous scholarship about this sculpture is only focusing on the written and printed paper, and they have never examined the materiality of the sculpture. So that's why they want to come to CNS and try to see whether they can try to see the interior of the sculpture. But engineer told us, whatever you're going to do, you can't touch the sculpture at all. So you can see, based on the dimension, you can see it's a very huge sculpture. It's almost like 68 centimeters in height and about 25 centimeters in X and Y direction. So based on the sample size and also the information we try to generate, and also the requirement that we can't touch the sculpture at all, the only way we can image this kind of sample at CNS will be using microcomputer tomography. So microcomputer tomography is also known as a micro-CT. So it's simply as a LED-based 3D non-destructive 3D imaging tool. So what you can do will be inside a micro-CT system, you're mostly going to see some kind of X-ray source on one side, and you also have a detector on the other side. So this guy is a flat panel detector. And we'll put the sample right in between these two components. When we turn on the X-ray, the cone beam X-ray is going to travel in a straight line perpendicular to the sample, and it will create some kind of shadow image on the detector. Sometimes we call this the shadow image as a projection image, or something we call it 2D radiograph image. But the detector can only capture the overall rows of intensity in one single direction. So eventually what you can do will be, we need to capture a different projection image at different rotation. So you can rotate a sample for entire 360 degrees and capture multiple projection images around your sample. So the result for the direct micro-CT scanning will be you're generating a bunch of 2D projection image around your sample. So for the entire micro-CT workflow, so what you're going to do will be, first of all, we're going to generate thousands of projection images around your sample. But by this time, all your image is still in 2D. In order to see some kind of 3D volumetric data set, we need to do some reconstruction using some algorithm. So once the reconstruction is done, then you can use your data for any kind of 3D analysis. So it's pretty much a very powerful, non-invasive and non-destructive technique to digitize your entire sample, either exterior and also interior information. So what kind of sample can you do on micro-CT? Since during the CT scanning, we are doing the scanning in ambient pressure and temperature, so you can literally do any sample you have in mind. So we're using micro-CT to do a lot of biological and anatomical studies. So on the picture on top here, that's a starfish, a projected image of a starfish. And right next to it is a section of a hairy spider leg. Down here is a cross-section image for the plant silent cell. You can also use microCT to do some kind of device and integration studies. Up here, the first image you are seeing here, that's a mouse head with some implants sticking out from the top. Down here, just a USB thumb drive we'll be using every day. Next to it is just a robot B from Professor Wu's lab here at SIS. We also done a tons of material and mechanical study using microCT. In the middle here, it just standard coke can, so try to squeeze the coke can a little bit and try to see how the metal deformed at different stage. And the picture next to it is just a filtered fiber from an encouraging particle in the middle from a Porsche car. Down here is a 3D printed foam, and the next one next to it is a hydrogel buckle. And due to the nature of the non-destructive capability, so we're also doing a lot of museum and archaeology studies. The picture right on top here is just a mummy mask from Egyptian mummy mask during the Roman period empire. And the next to it just a simple human skull. So you can see we can do a very wide range of variety of sample. The sample can be immersed in water, so you can have a sample inside the water and do the CT scanning. And as long as you can fit the sample into a microCT chamber, that's almost any sample you can do can be done at microCT. So let's take a brief look about how microCT have been developed over the years. So since we're using X-ray to generate some kind of image, so it all started from 1895 when Wilhelm Röntgen first discovered X-ray. And you can see the picture up here. That's the world's first 2D radiograph image from his wife's hand. So X-ray is just simply part electromagnetic spectrum here. And you can see from the spectrum on top here, our visible light is somewhere in the middle between 380 to 760 nanometer. And X-ray is sitting slightly with higher energy, but shorter wavelength. So usually it's between 0.01 to 10 nanometer. Most of the time, we will subcategorize your X-ray into two soft X-ray and hard X-ray, and they are pretty much differentiated by their energy range. So starting in 1970, we start to Hans Field from a British scientist start working on some kind of clinical diagnostic tool. He called it a brain scanner while he's still working at EMI. Yes, that's the same company that making all the Beatles records. So actually, you can also say all the Beatles is supporting the microCT development over the years. And eventually, Hans Field together with Alan Comet, a South African scientist, later he become a faculty around the corner at Tufts University. They have been awarded with Nobel Prize in Medicine and Physiology in 1979. So that's how the microCT has come from. And right now, there are two main flavors of CT machine you can find in the world. The first one is called medical CT. Some people call it CAT scan, and the other one will be microCT. That's a topic we are going to discuss today. So, starting in 1980, a lot of performance improvement have been done on the CT machine. So mostly will be improving the resolution and also reducing the acquisition time. So both medical CT and microCT, they are very much based on the X-ray transmission. So you need to make sure your X-ray can be transmitting through your sample. But the main difference will be the way we try to capture the data. So for just like you can see, for microCT, we need to rotate the sample 360 degrees. But for medical CT, it's very unlikely you're going to rotate the sample, which is the patient. So that's why for medical CT, we're using some kind of gantry. So the X-ray source and detector will be housed inside gantry, and it's going to rotating around the patient. During the scanning, the patient also moving in and out of the gantry. So eventually, what you're going to see will be some kind of spiral way of scanning. We call it helical scanning. As for the micro CT, we're using some kind of micro focus X-ray source. So that's why I give you much more flexibility with a larger range of scale and dosage. Before we dive into the discussion about micro CT, let's take a moment to talk about synchrotron and nano CT. That's all where the high resolution CT image is coming from originally. So synchrotron is just simply a gigantic particle accelerator that's first built in around 1940s. So starting around 1980, people have started to demonstrate they can capture some kind of nice CT image as synchrotron. So the main difference between synchrotron and the micro CT we are using will be for synchrotron, they are using parallel microchromatic X-ray source. So which means they can provide much higher flux and brightness and also the energy is pretty much tunable. So the schematic on the right-hand side here, you can see that's a schematic for a typical synchrotron facility. So they're using some kind of bending magnet and some kind of insertion device to generate X-ray. And down here, the picture is just a third generation of synchrotron in Switzerland. Nowadays, you can allocate some kind of a lead-based nano CT machine from some vendor. So for a true nano CT machine, what you're going to do will be you need to use some kind of X-ray optics. So you can see from a cartoon on the left here, we need to implement some kind of Branson zone plate lens and also condenser lens in order to give you the nice image. And usually for a true nano CT machine, the resolution should be, we can go all down to around 15 nanometer. So now let's take a first component, the major component we are using for the micro CT machine. It will be the X-ray source. So right now there are two type X-ray source you can use inside a micro CT machine, and they are pretty much different by their geometrical shape. So the first one is called the reflection X-ray source.
I don't understand why I cannot get. You know, when you use the word sacrifice.
So the X-ray source is arranged in some kind of elbow shape, and everything inside X-ray source is under vacuum. So what we're going to do will be we'll fire the filament with some voltage and current, and you will generate some kind of terminal electron at the tip of the filament. And the electron will be traveling at high speed inside the vacuum chamber, and eventually it's going to bombard it on a piece of metal. The metal will call it target, and it's going to generate some kind of cone beam X-ray. Eventually, the cone beam X-ray is going to emitting out from the aperture up here. The aperture is simply a piece of barrier window, and sometimes we might need to implement some kind of filter, which I will talk more about in a couple slides down. The nice thing about using the reflection X-ray source will be it can give you a much larger excitation volume, so you can have a higher intensity for your X-ray beam, but you're using a larger spot size, which means you're losing the resolution. The second type of X-ray source we call it transmission X-ray source. Now you can see the entire X-ray source arranged in the horizontal direction, and we're still generating the terminal electron on one side here and traveling in a horizontal way and hitting on a piece of metallic foil, and the X-ray will be coming out from here. So usually for transmission X-ray, you can you're using a smaller spot size. And that's why usually transmission X-ray source can give you a better result than comparing to the reflection X-ray source. But we're losing the intensity. So that's why usually for the transmission X-ray source, the intensity for X-ray gun will be much lower compared to the reflection X-ray source. And that's the X-ray spectrum that emitting out from your X-ray gun. So the graph down here, you can see is intensity versus the energy here. And you can see almost like 90% of our X-ray being coming out from the X-ray tube. It's just some Brownstorm, some people call it some dark radiation. So it's not very useful. So it's only 5% that considered some characteristic radiation from your target material. And when we do micro CT imaging, what we're going to do will be we'll try to adjust the parameter. So we try to manipulate in this spectrum to get a nice spectrum that's suitable for the material you're working on for the imaging. And the first parameter we're going to talk about is the acceleration voltage. When you try to change your acceleration voltage, you try to changing the maximum energy that's going to be coming out from your X-ray tube. So from the graph down here, you can see we try to change the X-ray energy, X-ray acceleration voltage from 100 kV over up to 200 kV. What the spectrum is going to do will be we try to shift the entire spectrum towards right and also moving up. When you try to increase your acceleration voltage, you're also increasing the amplitude at every energy. So that's why if you're working on some very dense material or a piece of metal, we will need very high energy, high voltage to get enough signal penetration through the sample. But by using a very high voltage, you are also increasing your your focal spot size. So which means you are losing the resolution. So the rule of thumb will be when you try to do some micro CT imaging, usually we try to use the minimum voltage we can use to get enough signal penetration through the sample. The second parameter you're going to adjust is called the filament current. So what the filament current is doing will be it simply try to increase your X-ray emission at all the energy. So which means you can get a much higher signal at every energy range. So that, again, from the X-ray spectrum, you can see the difference between 100 microampere to 200 microampere. So the nice thing about using a higher current will be you can try to improve your contrast and your intensity without increasing your X-ray spot size. Also, by using a higher current, we can try to extend the projections image histogram. So the wider we can try to spread out the histogram, the easier for you to differentiate different material inside your sample. So again, the rule of thumb will be when you try to do some micro-CT imaging, we'll be trying to use the current as high as possible before you saturating any background image. There are multiple methods that can be used as a target material to generate X-ray. So here I list a couple of methods you can see here. Most of the time, we just use some kind of metal with some high atomic number. And tungsten is the most common metal we'll be using over time for micro-CT. But occasionally we might be switching to another metal. For instance, a lot of time we might switch into a molybdenum right here that can give you better contrast for some biological soft tissue sample. And the second major component we're going to discuss definitely will be the detector. So how does our micro-CT detect the signal from your X-ray beam? So we'll be relying on some kind of solid state scintillator material. So you mostly composed of calcium iodine or some kind of calcium tungsten. What this kind of material is doing will be you are absorbing your X-ray signal and converting it into some kind of visible light. So there are two main detectors people have been using nowadays for micro-CT imaging. The first one will be you have a piece of zinc phosphor attached to the CCD camera using some kind of fiber optical array. So once the scintillator material detecting your X-ray signal and converting to some visible light, and you will just be detected by the CCD camera. That's the way we do it using the flat panel detector. But you also have another way to detect your signal. We'll be using some kind of optical lens. So before the signal being read out by the CCD camera, we can use some kind of optical lens to do another second stage of magnification. And that's the detector we are mostly used for generating some kind of high resolution CT image. The scintillator material, the response for CT material is not uniform and also degrade over time. So most of the time you need to take some kind of background image, such as white field correction and dark field correction, before you take in your projection image. So all the final projection image you are reading from the micro-CT dataset will be subtracting all this background image. Earlier I mentioned about the filter. So the X-ray source we are using for the micro-CT imaging is not monochromatic X-ray, just like the way they use for the synchrotron. It's a polychromatic X-ray source, which means it gives you a spectrum of energy from low to high. But if you're working on a piece of metal that's very dense, you only require high energy X-ray to get signal penetrate through the sample. The low energy X-ray is not going to penetrate through the sample, but you pile on the surface and create some kind of R effect. So in that case, we need to implement some kind of filter to filter out the low energy X-rays. So what the filter is doing will be you simply try to increase your average energy of your X-ray spectrum. So you can see from a graph down here, we have different filter. Filter 3 have much more stronger filter compared to filter 1. And just switch the spectrum towards the right here. By using the filter, we also reduce the signal intensity. So most of the time, if you're using some kind of filter, you might also need to boost out your filament current and acceleration voltage. As for the filter, we are mostly just use some kind of thin metal film, such as aluminum, copper, silver, and tin with different kind of thickness. But nowadays, we're also using some kind of composite material to do the filtering. So by now you already know when we do the micro-CT imaging, we are all depending on how much your X-ray has been absorbing into your sample. So we need to know how does the X-ray attenuate inside a material. So X-ray is attenuated inside a sample simply by absorption and scattering. So depending on your X-ray energy, if your X-ray energy is low, usually it's below ionization energy, what you're going to see will be you're going to see mostly some kind of coherent scattering. So what is coherent scattering will be, I'm using some kind of atomic model right here. The X-ray beam will come into your atom here and will be scattering out. So the energy scattering out is almost identical to the energy going in. But when you try to increase your X-ray energy, what you're going to see will be you're going to see some kind of quantum scattering. So what the X-ray beam is doing will be it's going to knocking out one of the outer shell orbital electrons, and eventually the beam will be scattering out. So now the energy being scattering out from your atom will be slightly will be lower than the initial beam energy. In between, you might also going to see some kind of photoelectric absorption. So which means the X-ray beam will be knocking out one of the inner shell electron and losing the energy. There's also another X-ray attenuation mechanism called a pair production up here, but it's very unlikely to happen during the micro CT scanning, because the pair production can only happen when the X-ray energy is greater than 1 mega electron volt. So to put this attenuation mechanism into some kind of mathematical model, so we can use Beer-Lambert law. So here is just a cartoon for certain material with a linear attenuation coefficient of mu and the mass density of rho, and the thickness of the sample is around x here. So the relationship between the intensity of the X-ray beam passing through the sample to the initial intensity can be simply described by this Beer-Lambert law, which means the signal actually is degraded exponentially. And if you try to divide your linear attenuation coefficient by the mass density here, you're getting the mass attenuation coefficient, and that's a parameter we are mostly dealing with when you try to compare different material inside your sample during the micro CT scanning. So here I'm showing you two graphs with different mass attenuation coefficient for two categories of sample, biological and non-biological. So for the non-biological sample, we just mean some pure elements such as tin, iron, calcium, silicon, and you can see they have different kind of mass attenuation coefficient. And for the biological sample, what we're dealing with mostly will be some kind of soft tissue, hard tissue like bones, and also water. A lot of time, the biological sample you need to immerse inside water. But you can see from the graph here, the mass attenuation coefficient for the water and the soft tissue is very similar to each other. So usually, if a piece of soft tissue immersing inside water and you want to get a very contrast, it will be very difficult to get good contrast from the soft tissue. That's why most of the time we might need to do some kind of staining. And you can see from the graph here, the most common staining we are doing here will be iodine. That usually have very high mass attenuation coefficient compared to the water and tissue. We'll talk more about the staining later. So how does our machine read out your linear attenuation coefficient? So it's all about the intensity the detector is reading. So on the detector, every pixel is going to give you some kind of value. That's a grayscale value. Just like you already can see, the projection image we're going to generate on the detector is a grayscale image. So every pixel is going to read out some kind of grayscale value. So so that's the intensity we're going to read out. And also putting all the background image I described earlier, the dark field correction and the white field correction. And we can calculate the mu multiplication of mu and x. Again, mu is our linear attenuation coefficient, and x is the thickness of the sample you're working on. So by calculating the multiplication of mu and x, you can try to generate an entire 2D image. And we have found out when your multiplication of mu and x is less than 2 for the longest hash length of your sample, you can get the best optimum micro CT image. Then we do the reconstruction, and now you are getting some kind of Foxhole number. Just be aware, the Foxhole number is different from the so-called Hounsfield unit. So a lot of people, when they come here and do a micro CT, they might say, I want to get some kind of Hounsfield unit. So it's different from the Foxhole number you are generating from the detector. And Hounsfield unit is simply a standard calibration scale for some medical image. But for this kind of scale, what they're doing will be they're using the air and water as your reference point. So for any user sample, if you are not using the air and the water as your reference point, you can't use the Hounsfield unit. Using Hounsfield unit won't be appropriate. And sometimes you might also need to get some kind of phantom if you want to do some nice calibration for certain material. For instance, now they do have a lot of very standard phantom you can get for some bone sample. Just like all the imaging modality, when you try to do micro CT imaging, we do need to improve the contrast sensitivity and also the spatial resolution. So micro CT, since we're using a cone beam X-ray source, so your data is going to be isotropic, which means every dimension XYZ, they are all in the same resolution. As for the contrast sensitivity, what we're going to do will be simply try to fine-tuning your acceleration voltage and filament current we described earlier. And so you can try to distinguish your feature away from your background image. For the spatial resolution, so for micro CT, the spot size for X-ray source is the absolute limit for the spatial resolution of the scan. So the only way you can try to improve your resolution will be simply try to bring your sample closer to X-ray source. So you can see from the cartoon here, so the source is our X-ray source, and here is our detector, and in the middle is our sample. So the way you can try to create some kind of magnification will be simply based on the formula here. So the magnification is equal to the distance between an X-ray source to the detector divided by the distance between your X-ray source to the sample. So that's, we call it geometrical magnification. So the better resolution you want to achieve, the shorter the distance for the A. So which means you need to move your sample very, very close to the X-ray source. So that's pretty much limited by your sample size. If your sample is gigantic, you just can't move your sample very close to the X-ray source. So that's why the major limitation for the resolution you will be able to achieve will be your sample size. And for some higher resolution micro CT machine, as I mentioned to you earlier about the detector, usually they are using another second stage of optical lens. So the optical lens can create a second stage of magnification. So which means your final magnification for your high resolution CT machine will be your first stage geometrical magnification multiplied by your second stage optical magnification. So eventually, the resolution you will be achieving will be the physical pixel size on the detector divided by your final magnification. And here is this contrast agent I mentioned earlier. So again, if you're working on some sample that doesn't have very good contrast, such as some low atomic number material, like carbon-based material, or some polymer sample, or even just some biological soft tissue, they don't have very good contrast on the CT image. So you might need some kind of contrast enhancement. So again, this is a couple contrast agents here. You can see most of the contrast agent actually we can see borrowed from the electron microscopic imaging. Again, iodine is the most common contrast agent we have been using here due to its simplicity and also low toxicity. So a lot of time, for instance, for some biological tissue, we might just be immerse your entire sample in some iodine solution for a couple of days. They dry it and do the imaging. Or if you're working on some animal, for instance, a lot of people here might want to see some kind of the microvasculature network inside the tissue. We just need to do some kind of perfusion to perfuse out all the blood inside your vessel. Then we perfuse the contrast agent into the blood. Then you can see the network for your entire microvasculature. Some people also using some kind of more exotic contrast agents, such as some nano micron metallic particle. So here I'm showing you two pictures from two different papers. The one on the left is some contrast agent staining using some osmium contrast agent for bumblebee head. So what the researchers they are trying to do for will be they want to do for different sections inside the brain. So after osmium staining, they will be able to distinguish a different section inside the brain. And the picture next to it, on the right here, is just another research for a piece of the mouse leg. And now they are using some kind of mercury chloride for the staining. You can see a clear difference before and after the staining. So before the staining, mostly you just simply see the bone, the hard tissue, usually very easy to see on the X-ray image. But once you do the staining, now you can see all those nice fiber inside your muscle. So again, if your research focus is on the tissue part, then you will definitely do some kind of staining. But if your research focus is only on the bones, then you don't need any staining. So all the discussion we've been going through so far is simply based on the traditional X-ray imaging, which means it's all depending on how much your material, your sample can be absorbing the X-ray beam. But when X-ray passing through a piece of material, as a cartoon showing down here, it's not only decreasing, it's not only in amplitude by the attenuation, but also delay the signal. So you have some kind of phase shift. So if we can capture the phase shift for this difference, we might be able to enhance the contrast And in the old day, you can only do this kind of face capture this kind of phase shift for X-ray imaging in a synchrotron facility. But nowadays, we can also try to implement this kind of capturing this kind of phase shift using some polychromatic X-ray cells in the lab. So we call it phase contrast imaging. So why does phase contrast imaging can help to improve your contrast? So the phase contrast change due to the rapid variation of the refractive index at the material boundary. That's why sometimes we call it a boundary effect. So you can see from the cartoon down here, it just simply a cross section for some kind of circular shape. So the graph, the B here, just simply the phase difference between the bin 0 to bin 2 here. So you can see the phase change the highest when the sample is thickest in the middle right here. But if you try to do some differentiation, now we are getting the phase gradient in the x direction. And by doing the second derivative, you can see the maximum show up only on the boundary of your sample. And that's why the phase contrast imaging will be able to help you to improve your contrast, especially on the boundary of your sample. There are two ways you can do the phase contrast imaging. The first way will be using some kind of grating interferometer. And you can only do this type of imaging in synchrotron. You require much larger distance between your sample to the detector. And what the interferometer is doing will be you're creating some kind of interference pattern. So you can try to pick up the difference between your reference signal and your sample signal. So which means if you are trying using this technique to do the phase contrast imaging, you definitely need to have some kind of reference image first. And the second type of phase contrast imaging will be doing so-called the propagation phase imaging, so also known as an inline holography. For this type of imaging, the benefit for this type of imaging will be you don't need any reference image. So you can see from the picture on top here, that's just our regular absorption image. So you're trying your sample with some X-ray beam and you create some kind of intensity difference on the detector. By moving the detector further away from your sample, now the X-ray beam, the signal needs to travel a much larger distance before you reach into the detector. So when you travel in larger distance, the tiny phase shift is going to expanding out. So we can start to pick up those phase difference between different signal. So now you can start getting some kind of brighter edge around your sample. And that's so-called the propagation phase contrast imaging. And for the LED-based micro-CT machine, that's what we're doing here. We're just moving the detector further away from your sample. But you can see by moving your detector further away from your sample, now your signal also getting lower. So which means most of the time we need to increase your scanning time much longer in order to compensate the signal decrease to the detector. Here is another two picture from two different papers. So the picture on the left is just a phase contrast imaging for mouse brain. So this data was taken from European synchrotron in France. So the phase contrast imaging for this research was done using the gradient. And you can see the picture underneath here. They are looking for a tumor inside the brain. But before you apply the phase contrast, it's really hard to find the specific location to the edge of the tumor. By using the phase contrast, now you can try to brighten out the edge of the tumor, then you'll be able to define the size of the tumor and so on. The second image on the right here is another image that's taken from a micro-CT. So this guy was based on the propagation phase contrast imaging. And the sample is a piece of mouse lung. So before you apply any phase, you can't see any difference in this region right here. But once you apply the phase, now we can start to see the difference between we can see two phases inside this region, and they are actually different by water and fat. So you can try to distinguish the water and fat by using the phase contrast imaging, which is really hard to see without any phase enhancement. So for micro-CT, we can also do so-called vibration contrast tomography. Be it for the absorption, the normal absorption image, and also the phase contrast imaging, it's all based on the material density difference. But sometimes if you're working on some single phase polycrystal, they don't have such difference. But if you want to see the grain boundary inside your sample, such as a piece of steel or maybe a piece of alloy, you might need some kind of diffraction contrast tomography, also called a DCT. So if you want to generate some kind of crystallographic information, DCT is the way to go. But you might say, I also can do generate some kind of crystallographic information from some optical microscope or even the 2D and 3D electron microscope such as the EBSD. But 3D EBSD is a destructive technique. You need to do some sizing and viewing, and DCT is the only non-destructive technique to give you some kind of crystallographic information. So what we're going to do will be inside a normal regular micro CT machine, you're going to implement another aperture inside the X-ray probe. You're also going to implement another beam stop before the signal go to the detector. What the beam stop is doing will be you will try to increasing your dynamic range for the diffraction detection. And usually when we try to do DCT imaging, we will try to do some kind of symmetrical geometry, which means your sample will be sitting right in the middle of the X-ray source and detector. They can help to improve the diffraction signal strength. So by using a DCT, you can try to learn the grain structure and also the quantify the crystallographic orientation relationship. So here I'm showing some data for the DCT imaging. So it's just a 3D grain map for a piece of titanium alloy. So you can see from the inverse pole figure, we can do some color coding for different grain inside your alloy. And the image on the right here is a comparison between the DCT measurement and also EBSD measurement. You can see the misorientation between the two measurements is very similar to each other. It's less than 1 degree difference. So that's pretty much everything about the micro CT scanning. And as I mentioned at the very beginning, the entire workflow will be once you're done for scanning, you still need to do the reconstruction. That's why you can see your image in 3D. I won't go into further detail about reconstruction. We just simply a bunch of mathematical calculation and formula. But the entire reconstruction all start from a random transform. That's has been first demonstrated by Johann Röntgen in early 20th century when he tried to reconstruct some cross-section image based on its projection image. So by taking the inverse or random transform and combining to the Beer-Lambert law we described earlier, we can calculate the attenuation coefficient for every voxel. Nowadays, mostly we're using some kind of filtering, back projection reconstruction for reconstructing all the micro CT image. Down here, you can see that's our dummy sample, a piece of square, and we try to reconstruct this image by its projection image with different number of projection. You can see as a number of projection increase, we can get a much better result. But we also have some kind of halo around your image. That's why we need to do the filtering, and eventually the final data will be looks much closer to your original image here. So I'm going to show you a couple of reconstruction artifacts that's mostly happen to some of our users over here. And some of these artifacts might be dedicated for the micro CT machine, but some artifacts can also be shown on your synchrotron or medical CT data. The first artifact is so-called motion artifact. By now, you already know during the scanning, we are going to rotate your sample 360 degrees. But you need to make sure your sample is stable inside the sample. So you need to make sure you can secure your sample on the stage very nicely. That's the reason when you go to a hospital and take some CAT scan, the doctor is always say, hold the brace, don't move. Any kind of movement is going to destroy your X-ray image. So you can see from this picture on the screen here, not just a cross-section image for a piece of sample, but you can look very closely over here. We do have some kind of double image, and down here, there's no double image. That's a clear indication the sample might be moving during the scanning. So that's so-called a motion artifact. Again, the motion can be any type of motion. It can be also some kind of thermal motion, or it can be maybe the sample can shrink over time, and the shrinkage will be also considered another type of motion. So you want to make sure your sample will be stable and steady throughout the entire period of scanning time. The second artifact is called the ring artifact. During the micro CT scanning, something is going to do a rotation. Either your sample is rotating or the the X-ray source and detector is in motion, the circular mode. And sometimes if the detector readout is have some kind of delay, you might see some kind of ring in the cross section of your image. So the two images are coming from the same sample, and you can see the sample should be uniform and homogeneous. But I purposely try to creating some kind of ring eye effect inside the sample. Now you can see all those eye effect that show up in your image. And the next eye effect is called the reconstruction center error. So depending on where you look your sample on the stage, if your sample is kind of a little bit off center, and when you do a full rotation, it might be showing you some kind of reconstruction center error when you do the reconstruction of your image. Sometimes the off center is not very much, it's only a couple pixels, the program might be still be able to do the reconstruction for you. But if the shifting is too much, maybe more than 200 pixels, now the program won't be able to reconstruct your image for you. So you can see now we just won't be able to reconstruct your image, even though from your projection image, it looks pretty nice, but we just won't be able to reconstruct into a 3D model. And earlier I already mentioned, the more number of projection image, the better your reconstructed result. So here just mean two comparison of two different images. The image is a medical CT image, but with different number of projection. You can see with a higher number of projection image, now we can see much greater detail inside your sample. So with a low projection image, we just call it undersampling issues. And the next eye effect is a bin hardening eye effect. That's similar to the filtering we are describing earlier. Again, if you are not using any filtering, and again, the sample should be a homogeneous, so that's a cross-section image. The sample should be homogeneous and uniform. That's what you can expect to see on the left here. But if you try you see your image has some kind of brighter ring on the outside and darker region in the middle, that might be some kind of indication. It doesn't mean your sample is not uniform. It might just mean you have some kind of bin hardening eye effect. So in this case, most likely you might need to implement some kind of filtering to improve your image quality. And the next eye effect is called the strip eye effect. That's mostly shown when you have two different materials inside your sample. For instance, the image you're seeing here, that's a cross-section image for a mouse cochlear bone and with some metal implant inside. So when we try to fine-tuning our acceleration voltage and film current, so we can get a nice contrast on the cochlear bones, but the setting might be it's not very suitable for the metal here. So now you can see all those scattering of the X-ray beam from the metal implant, and that's called the strip eye effect. And the last eye effect I'm going to show you is called the phase contrast eye effect. Earlier I mentioned the phase contrast can help you to improve your image quality, and you can reveal some tiny detail which you might not be able to see from some normal absorption image. But sometimes it can also give you some kind of eye effect you don't want to see. So for instance, on the picture here is a comparison for a mouse brain. On the left here, it's just a standard absorption image with the iodine solution staining. And on the right here is using phase contrast imaging. Now you can see with the phase contrast enhancement, we can see those tiny detail inside the brain here. But if you try to see the outer ring of the brain here, you can see that it's kind of a little bit brighter. That might be pretty much due to the phase contrast eye effect. It might not be real in your sample. It might pretty just thinking phase contrast eye effect, which you can do some correction later. So that's a couple of typical eye effect you might be seeing when you do some micro CT scanning. And by the time you're done for scanning and reconstruction, your data is ready to use for 3D analysis. So most of the time, now by this time it's a 3D photometric data, so you can try to view your data in some kind of volume rendering or surface rendering. You can try to adjust in some kind of viewing threshold, so you can try to focus on different regions. For instance, the picture on the top here, we try to focus on those soft tissue in the mouse here. And down here, we try to focus in on those skeleton, the bones inside the mouse. And at CS here, we are also using some kind of commercial program that can help you to working on all these kind of 3D data set. And at CS, we have do a couple programs that's available to the user. So we have VG Studio Max from a company called Photon Graphic. We also have Aviso from Thermo Scientific, and also have Dragonfly from ORISE. So we have these three programs at CS here. And across the street, the OED department, they also have another site license for the Mimics. And I just done a couple months ago. Our neighbor at the Brigham Women's Hospital, they also have another 3D viewer called 3D Slicer. And I heard it's a free download program, so the user can also try out on this program and viewing any 3D photometric data. And one of the usage for your any 3D data will be sometimes you want to do some kind of segmentation, and also known as a labeling. So you try to label a couple pixels inside your 3D data set. So which means your sample definitely consists several discrete phase with distinct absorption or phase contrast. That's why you will be able to differentiate different regions and do some kind of segmentation. Nowadays, we're also using some kind of artificial intelligence algorithm. You can do some kind of machine learning, try to train the machine to help you do some kind of segmentation using the computer. So the picture down here is just a picture for micro CT scanning for a frog from Florida Museum. So what they're doing will be they try to segmenting out the central nervous system from the brain all the way down to the spinal cord and to all the nerve fiber here. And the picture on the right here is another scanning. The sample is coming from MEEI. So this guy is a sheep cochlear bone. So yeah, we're doing a lot of cochlear bone scanning, the mouse, sheep, monkey, human, and this guy actually is a sheep cochlear bone. The sample size is around 40 millimeter across the sample, and we try segmenting out the cochlear bone right in the middle of the sample and do some color coding. You can also using your 3D data to do any kind of data analysis. Over here as engineering school here, a lot of people working on some fiber material, so they might want to do some kind of fiber analysis. You can try to find out the orientation for every piece of fiber inside the sample. You can also try to find out the connectivity between the fibers. You can also do some kind of transport analysis. So the picture on the right here, that's another sample from one of our users here. So what he is doing will be he wants to study the physical link between the subsurface fluid injection to some kind to the earthquake. So that's why we do some kind of using some kind of lab simulation model here. The sample have different zone of material. So we try to inject the liquid from the top here and try to find out how the liquid sneaking through the entire different layer of material and eventually going out here. And so you can try to test some micro CT before the liquid injection and also after liquid injection. So the liquid we're using some kind of iodine solution that can help us to enhance the contrast. You can also do some kind of dynamic structure analysis, which means you also involve in some kind of time. So you can have some kind of external stimulation, maybe temperature, maybe the force, and see how your material change based on your stimulation. And the 3D data can also be used create some kind of animation. So the sample is some kind of calcified osco from one of our users here. The sample size is about a couple millimeter in the horizontal direction. So we try to do 2 micro CT scanning. The first scan using the lower resolution is about 1.3 micron for each voxel. And once the high resolution, the lower resolution is done, then we zoom into certain region right in the middle and performing much higher resolution scanning. Now each voxel is about 515 nanometer. Then from the high resolution scanning data set, we can try to do some kind of data analysis. For this data, we try to find out the different thickness at different region. And that's another sample from one of our users here. So he's working on some porous ceramic material for some kind of catalyst emission control application. The first guy here is just some of our micro CT data. And here is they try to determine the pores inside the material using again one program called Aviso. Once you have this data, and he tried to combine the Aviso data and some consoles, they can do some kind of simulation and to see how certain either some fluid like liquid or air can be flowing through the material. So by coupling the microstructure analysis and the flow simulation result, we can allow us to try to do some structure flow relationship, and that will help them to design different kind of catalytic for this kind of material. At CS now, we also have a well-established workflow, so you can do some kind of correlative imaging. So the data is coming from one of my colleagues, Stephen. So what we're doing will be, he's working on some kind of malaria parasite in the mosquito. So what we're doing will be, and he wants to get very high risk. He wants to go to some specific location inside the parasite, but it's very hard to go to specific location just simply looking under the electron microscope. You do need a very high resolution. You need nanoscale resolution. So what we're doing will be we try to do some micro CD for the entire sample. So the sample has been fixed and stained in some kind of epoxy, and then based on the coordinate we generate from the micro CD scanning, you can use the same coordinate and bring the coordinate into his focus ion beam, so you can go to certain location and find the exact location for the target parasite and perform some kind of size and viewing, as you see here on the picture here, to the tip of the parasite he's looking for. So now we have a well-established workflow, so you can simply go from a very micro scanning for your entire sample, then zoom into a certain very specific region to get a very high resolution image. So that's pretty much everything about my presentation today. So that's compared to our earlier case study. So again, the Prince Shotoku. So we try to do a micro CD scanning for the entire sculpture, and due to the size of the sculpture, we need to do 5 different sections of imaging and try to do some manual stitching later. So now we digitize the entire sculpture, so you can try to view your sculpture in all different orientation. You can try to open up sculpture and try to see what's going on. So for instance, if you try to cut the sculpture in the coronal plane, you can try to learn how the sculpture have been constructed and built. So you can see they do put 2 wood pin right here. So the 2 arm actually is being made separately, and they use the wood pin to join the arm and the main body. And if you try to carve in the sagittal plane here, now you can see we do find 2 smaller ridge right in these 2 locations. So the history for this sculpture will be in the early 20th century. Somebody from the Museum of Fine Art in Boston, they tried to open up this sculpture and take out all those 70 object inside. So, but they didn't make any record about how they open up sculpture from the bottom. So we found out from the wedge here. It turned out, I think we seen in the beginning that definitely has some kind of shell, multiple shell inside the sculpture. And we also see how they try to carve the wood from the bottom. And we also, based on the growth rate of the wood, and we try to flip the top portion of the wood, that's the front part, and try to align to the bottom part here. You can see the growth rate actually align to each other very nicely. So which means actually the entire sculpture is coming from the same piece of wood, and it's cut into 2 pieces, one part for the front side and the other part for the back side. So that's pretty much everything. And so at CNS right now, we have 2 micro CD systems available to the user, and they are coming from different vendors. So the one on the left is a Nikon machine, and the one on the right is a Zeiss machine with different kind of resolution. So the Nikon is an older machine, but it has larger chambers there, so it can handle a much larger sample size. Also, the Nikon machine will still have different target material that's available for different imaging. For the Zeiss machine, it give you very high resolution imaging. Usually, we say the best resolution we can achieve on this machine is about 400 to 500 nanometer. And for the Zeiss machine, we can also do phase contrast imaging I described earlier, and also diffraction contrast imaging. We can also do some kind of in situ mechanical and temperature testing inside the chamber. So if you are interested to do any micro CD imaging, and feel free to contact me.